All right, hello again. In this section, we're going to learn about another class of equations. They're called first-order linear equations, and we're going to see the method that we can use to solve them. We're also going to see an application. We're going to look at a mixture problem again, but this time, when writing the differential equation, modeling the mixture problem, we'll end up with a linear equation that we will then know how to solve. All right, so some new terminology. Linear, I don't think we've introduced that phrase. So linear refers to the fact that in a linear equation, the dependent variable and its derivatives are only raised to the first power. And we've seen the idea of first order already. First order refers to, again, that the highest order of the derivative is 1. So the general form for a first-order linear equation is y prime, right, the first derivative of y, plus some p of x, some function of x, times y is some other f of x. So again, the dependent variable is y, right, dependent, and there's its derivative, and those are only raised to the first power. And the highest order of the derivative is 1, right? We only see the first derivative. We don't see any second derivatives or higher derivatives. If we do, we have to do something else. Now, it turns out for equations of this form, the separation idea that we've already learned generally doesn't work. Let's consider this example. Let's say we had xy prime plus 3y is x to the fifth. So we rewrite this as x times dy dx plus 3y is x to the fifth. Well, if I try to multiply by the dx, if I try to get rid of the dx, x dy plus 3y dx is x to the fifth dx. So notice I have an x dy, notice I have a y dx. That's not good. And there's nothing algebraically that I can do to force the separation. So separation doesn't work. We have to use some other method. So let's see that method in action, and then I'll go back and sort of explain why it works. So here's that equation again. And what I'm going to do with this is, first thing I want to do, I'm going to divide by x. I want that y prime by itself. So I'm going to divide each term by x. So now I have y prime plus, and what I'll do is I'll write this term as 3 over x times y, and then the right-hand side is x to the fourth. Simple algebraic move there. Now what I'm going to do is I'm going to multiply both sides by x cubed. Why? Trust me. For now, I'm going to explain where that came from in just a couple minutes. Okay, so if I multiply through by x cubed, let's see, that's going to give me then x cubed y prime plus 3x squared y is equal to x to the seventh. And now look at this carefully and think back to Calculus 1 for a moment. So now I want you to look at this expression right here. Look at the left-hand side and think back to Calculus 1. Doesn't that sort of look like a product rule? Right? If I sort of think of, right, so remember the product rule for derivatives said that the derivative with respect to x of f times g, where f and g are functions of x, was f g prime plus f prime g. Right, so hopefully you've seen that product rule. Maybe it was presented slightly differently, but hopefully you've seen this idea. I really hope you've seen this idea before. So now notice x cubed y prime. Notice that the derivative of x cubed is 3x squared, and the derivative of y is y prime. So isn't this left-hand side, isn't this the derivative with respect to x of x cubed times y? And that's equal to x to the 7th. So the derivative of this product is x to the 7th. Well, now I apply the integral. Let's now find the antiderivative of each side. So the antiderivative of a derivative sort of undo each other. I know I have x cubed y is equal to, the antiderivative of x to the 7th is 1/8, x to the 8th. Let's remember that we'll have a constant from integration. And then to solve for y, we just now divide by x cubed. Divide by x cubed, divide by x cubed. And so then we end up with y equals 1/3, I'm sorry, not 1/3, 1/8, x to the 5th, plus, let's say, I'll write that as c, x to the -3rd. There's the solution of the differential equation. And we can easily check this, right? If that's my y, then I can calculate the derivative. Y prime would equal 5/8 x to the 4th minus 3c x to the -4th. And I can substitute into the original equation x times y prime, x times 5/8 x to the 4th minus 3c x to the -4th plus 3 times y, 3 times 1/8 x to the 5th plus c x to the -3rd. And the question is, of course, is this equal to x to the 5th? This should work out. So let's see, that would give me 5/8 x to the 5th minus 3c x to the -4 plus 1 is -3rd plus 3/8 x to the 5th plus 3c x to the -3rd. The x to the -3rd terms are opposites. They add to 0. And let's see, I have 5/8 plus 1/8. That's 8/8 x to the 5th, which is certainly 1 x to the 5th. It checks out. So I'm confident in the solution. So then again, the process was, I took my original equation and then I divided by whatever was in front of the y prime. In this case it was x. I divided through by that. Then I used some trickery. I multiplied both sides of the equation by some number. In this case the number was x cubed. And I said, well, where did that number come from? We're going to get there in just a moment. We multiply by that x cubed, and then something nice happens. The left-hand side of the equation became a derivative of a product. And so if I can rewrite that as the derivative of a product, then I can calculate antiderivatives and find the explicit solution. So now let's go and explain, where did that x cubed come from, and is this something we can use generally? Alright, so now where did that x cubed come from? Alright, so recall that the equation, after we divided through by the x, we had y prime plus 3 over x times y is equal to x to the 5th. And now what I did was, I took that 3 over x, I took that plus 3 over x, and I used it to create what's called an integrating factor. And to find the integrating factor, what I did was, and I'll call it r of x, the integrating factor r of x turns out to be e raised to the power of integral, in this case of 3 over x, dx. And so the integral of 3 over x, that's e to the natural log, e to the 3 natural log absolute x plus a constant. Now here the constant isn't too important, it can actually be any number, so we're going to choose, let's choose c equal to 0. Turns out it works out okay. And so now my r of x is e to the 3 natural log absolute x. Well, let's also assume that x is positive. It's a simplifying assumption. If we assume x is positive, then r of x is now e to the 3 just natural log x, right? Because if x is positive, we don't need the absolute value anymore. Remember a rule for logarithms. I can now rewrite this as r of x is equal to e to the natural log of x cubed. And if you remember that the exponential function and the natural logarithmic function are inverses, and they undo each other, and so then r of x is x cubed. And that was the integrating factor, and that's what I multiplied both sides of the equation by to make it work. Now let's see, why does it work? Where does this integrating factor formula, where does this come from? Why was I able to use this e raised to the power of the integral of that 3 over x dx? Why does it work? So now why does it work? Well, let's assume for a moment that it works. I mean, we've seen it work. And let's see why it works. Why does it work? Okay, so let's start with our general form. We have y prime plus some p of x y is equal to some f of x. So what I'm going to do now is, if I assume this method works, let me multiply both sides by this integrating factor. Multiply by some r of x. So then I'll have r of x y prime plus r of x p of x y is equal to r of x f of x. Now we've seen the method work, and we saw, okay, if it works, then I need this left-hand side, you need this to be a derivative with respect to x of some r of x, whatever that r of x is, times y. I need that to work. Well, if I calculate the derivative of r of x y, right, so if we calculate this derivative, that would be r of x y prime plus r prime of x y. So I need that derivative to be the same as the left-hand side. I need that to equal r of x y prime plus r of x p of x y. And if we just sort of equate the terms, right, notice, a couple of the terms match up. See, we have the r of x y prime matches up with the r of x y. That's good. The other terms, they aren't quite right. We need them to be equal. So now we need r prime of x y to equal r of x p of x y. I can divide through by y on both sides. And so now I have r prime of x must equal r of x p of x. And so now I can separate the variables here. Remember that r prime of x is dr dx. So I have dr dx is equal to r of x p of x. And so I have 1 over r dr is equal to p of x dx. And I can integrate both sides of this because now it's separated. And so now integrating both sides. Let's throw in an integral symbol here. Let's integrate both sides. Well, that's natural log of absolute r is equal to the integral of p of x dx. And if we go through some manipulations, our standard manipulations, and we just sort of adjust it for the constants. The constants we can choose to be whatever we want. And from this, exponentiating both sides, we find that r is e to the integral of p of x dx, which is that integrating factor. And so what we now know is, in general, if we have this equation, if we have our linear equation and it's in this standard form, what we want to do is we want to multiply by the integrating factor, where that integrating factor r is given by e raised to the integral p of x dx. So we have to figure out what this p of x is, and we then go to and use it to find the integrating factor. Let's see a couple more examples of this technique. Alright, so let's solve the equation. Y prime plus 6y is e to the x. Alright, so notice that this equation is already in the standard form. Y prime plus some p of x times y is equal to some f of x. So the p of x is this plus 6. Right? P of x from that form in the earlier slide is 6. So then the integrating factor, then the r of x, would be e raised to the integral of 6 dx. And so that would be e to the 6x. And again, we don't worry about the constant. Don't worry about the plus c. We can choose the c to be any number we want. We choose it to be 0 in this situation. Alright, so now what I do is I multiply both sides of this equation, multiply by e to the 6x. So that gives me then e to the 6x y prime plus 6 e to the 6x y is equal to e to the 6x times e to the x. That's e to the 7x, isn't it? Now, if we've done this correctly, then the left-hand side should be nice. The left-hand side, let's check this. Is it the derivative with respect to x of, let's see, we would have to have e to the 6x and y. Let's make sure we did that correctly. Let's think of the product rule here. The first, leave it alone, the derivative of the second, e to the 6x y prime. That checks out. Plus the derivative of the first, e to the 6x, its derivative is e to the 6x, and then from the chain rule we need the 6. And we leave the y alone. It works. So then this is then equal to e to the 7x. We find antiderivatives. The antiderivative of the derivative, that's e to the 6x y, and the antiderivative of e to the 7th x is 1/7 e to the 7x plus a constant. Now we need that constant there. We can't make any assumptions about it yet. Alright, and then from here we solve for y. Divide through by e to the 6x, which is the same as multiplying by e to the negative 6x. Y is 1/7 e to the x plus c e to the negative 6x. And there's our solution. So again, the process. Figure out the p of x, create the integrating factor, multiply through both sides by that integrating factor, check to make sure you did it right, make sure that that left-hand side is the result of a product rule, and then use it to solve, right? Find antiderivatives and find the explicit solution. Let's see another example. So we were asked to solve t dy dt plus 2t squared y is equal to t squared, and here we're given an initial value. So this is an initial value problem. Y of 0 is 1. Now again, this would be a good time to maybe pause. Try this one on your own before you watch me do it. Alright, so first thing I'm going to do is I'm going to divide through by t. I want the dy dt, I want the y prime by itself. So let me divide through by t, divide through by t, divide through by t. Alright, so now I have y prime dy dt plus 2t y is equal to t. Let's calculate the integrating factor. So the integrating factor, r of t, we'll call it, would be e to the integral of 2t dt, just using t instead of x. And so that would be e to the t square. That's the integrating factor. Multiply through each term by the e to the t square. So I'll have e to the t square y prime plus 2t e to the t square. Oops, hit the wrong color there, sorry about that. E to the t square times y is equal to t e to the t square. Let's see, what's the left-hand side? Does that work? Let's think of the product rule. The derivative of e to the t square. What's the derivative with respect to t of e to the t square? Let's see. That would be the derivative of e to a power is e to the power times the derivative of the power times 2t. And notice that that 2t e to the t square shows up here. This looks good. So this left-hand side is d by dt of e to the t square times y. And the right-hand side is just t e to the t square. So we've brought in the integrating factor, it checks out. Now we need to integrate both sides of the equation. Integrate, integrate. The integral of a derivative, they undo each other, so I have e to the t square y. Now the right-hand side, the antiderivative of t e to the t square. You'll have to make a substitution here. Right? If you make the substitution, if we and I guess I should have a dt in there somewhere, but let's let u equal t squared, then du is 2t, so I need a 1/2. So this gives me a 1/2 e to the t square plus a constant. And I'll divide through by e to the t square, which is the same as multiplying by e to the negative t square. Y equals 1/2 plus c e to the negative t square. So there's the solution to the differential equation. Let's remember, though, I have the initial value y of 0 equals 1. So then that means that 1 must be equal to 1/2 plus c e to the negative 0 square. E to the 0 is 1, so 1 is equal to 1/2 plus c, and c ends up being 1/2. So then, revising the solution, y is equal to 1/2 plus 1/2 e to the negative t square. And so that is the solution of the initial value problem. Let's finish off this section with a mixture problem, another application here. Here we're told a large mixing tank initially holds 300 gallons of water in which 50 pounds of salt has been dissolved. A brine solution with concentration 2 pounds per gallon is pumped into the tank at a rate of 3 gallons per minute, and the well-stirred solution is then pumped out at a faster rate of 3.5 gallons per minute. So notice this one's a little different than the ones we saw in the separable equations. The main difference is, in the one we saw in the separable equation, the rate in and the rate out, as far as the liquid, it was the same. They were pumped in and pumped out at the same rate. We don't have that here. They're being pumped in and out at different rates, and when that happens, generally speaking, we're not going to have a separable equation. Alright, so let's determine a dE. Let me introduce some variables here. I will let A be a function of t, and we'll let A be the amount of salt again, amount of salt at time t. Alright, and the amount of salt, that's going to be in pounds, and time t isn't going to be in minutes. Alright, so remember, the general idea is the rate ends up being the rate in, take away the rate out. What's coming in, what's going out. Remember, R, and that shouldn't be dr dt, that should be dA dt. Okay, remember the units. A is in pounds, T is in minutes. So this has to, work out nicely. All right, the units have to work out nicely. dA dt. All right, what's coming in? Let's see, what's coming in? Well, it's coming in at a rate of 2 pounds per gallon. And into the tank at a rate of 3 gallons per minute. All right, so the gallons reduce out, and so that's nice. Then it's leaving. What's leaving? Well, some amount of salt is leaving. We don't know what the amount of salt is at time t, but we're calling it A. So we have A pounds, and the tank initially holds 300 gallons, but it's not holding steady at 300 gallons. Let's think about this. Fluid's going in at 3 gallons and leaving at 3.5 gallons per minute, so there's a net change of 0.5 gallons per minute. So the volume of the tank starts at 300 gallons and is reducing by a ½ gallon per minute. 300 minus 0.5 T. That's the volume in the tank at any time. All right, so what's leaving the tank? A pounds per 300 minus 0.5 T gallons, and it's leaving at a rate of 3.5 gallons per minute. All right, so remember this. Remember, A is a number of pounds, and the 300 minus 0.5 T, that's going to be a number of gallons. Again, the gallons reduce out, and we do end up with pounds per minute. A little bit tougher, though, than the example we saw previously. And so now I can rewrite this. Let's just clean it up a little bit. I have dA dt is equal to 6 minus 3.5a over 300 minus 0.5 t. Now, I could work with this, but I've got these decimals. I don't want to deal with those decimals. I'm going to multiply that second fraction, just this fraction. I'm going to multiply it by 2 over 2. I'm multiplying by 1, but that simplifies things a little bit. That gets rid of all of those decimals. It just makes life a little bit easier. So let's see, I have A prime is equal to 6 minus, let's see, this is 7a over 600 minus t. And I switched out that dA dt with an a prime. Notice now I can rewrite this in the linear form. A prime plus 7 over 600 minus t times a is 6. And I see that this is now linear. And so now let's work with this equation. Let's solve this equation and come to a solution. Okay, so the first thing I've got to do now is find the integrating factor. So let's find the r of t, I should say. The integrating factor r of t would be e to the integral of 7 over 600 minus t dt. All right, so let's see. Integral 600 minus t. So that's going to give me a natural log. I'm going to have a negative in there somewhere, right? Since 600 minus t and not t minus 600. So this is then e to the negative 7 natural log of, let's not worry about the absolute here. Let's assume t is positive, all that sort of things. 600 minus t. we use our properties of logarithms, and that's e to the natural log of 600 minus t to the negative 7th, and e to the natural log, they undo each other, and so that's just 600 minus t to the negative 7th power, and that's my integrating factor. So let's multiply through both sides of the equation by the integrating factor. So I now have 600 minus t to the negative 7th a prime, and now I have 7 over 600 minus t. That's 7 times 600 minus t to the negative 1st times 600 minus t to the negative 7th. So this is then plus 7 times 600 minus t to the negative 8th. A is then equal to 6 times 600 minus t to the negative 7th. It's really messy, but it turns out very nice. The left-hand side is d by dt of 600 minus t to the negative 7th times a, and the right-hand side is just 6 by 600 minus t to the negative 7th. We integrate both sides of the equation with respect to t, of course. So the left-hand side is just 600 minus t to the negative 7th times a. Now the right-hand side, you'll have to use a little bit of, you might have to use a substitution, but techniques that you learned in Calculus 1 will integrate this just with a simple substitution. So if you make the substitution, if you let u equal 600 minus t, and du is negative dt, we end up with 6 times, we would need a negative, right? Because the du is going to be negative dt, so negative 6. We'd have a 600 minus t to the negative 6th over negative 6 plus a constant. Right, it's just ends up being a power rule. The negative 6's reduce out, so I now have 600 minus t to the negative 7th times a is 600 minus t to the negative 6th plus a constant. I can solve for a by multiplying through by 600 minus t to the 7th. A is then equal to 600 minus t to the 1st power plus c times 600 minus t to the 7th. Okay, we have this, but now we must remember that there was an initial value. Maybe we should have written that back up here. So notice, originally there's 50 pounds of salt. So that tells me that A of 0 is 50. Sorry about that. So A of 0 is 50. So that means then that 50 must equal 600 minus 0 to the 1st power plus c times 600 minus 0 to the 7th. And we can solve this for c. 600 minus 0 is 600. So subtract the 600, negative 550 is equal to c times 600 to the 7th power. And so c is negative 550 over 600 to the 7th power. And I calculated this earlier. This is approximately negative 1.96 times 10 to the negative 17th power. It's a pretty small number. And so we end up with our function at the end. A of t is, what was it? It was 600 minus t, and c is negative, so let's write this as minus 1.96 times 10 to the negative 17th times 600 minus t to the 7th. So there we have it. There's that solution for the equation, and that's what gives us the, that's what models it algebraically. And notice one thing. Notice that if t equals 600, notice that a of 600 is equal to 0. After 600 minutes, the tank is empty. There can't be any salt in it. So that's a reasonable thing to notice, right? After 600 minutes, the tank's empty. And so there can't be any salt. All right, so I hope this gives you a good idea of how to solve some linear equations, and go in and practice it. All right.